Do you remember UC? Yeah, UC, Bu UC, your former students from ITB,
Of
from
course, Yuzi,
Padjadjaran,
of course, of
Yeah,
course.
yeah.
Ivati, yes, of course.
He will come here as well to join us, and
Yes. You have a very nice paper on the peroxidases, manganese
yeah,
compounds.
Manganese compound. Yeah.
Yeah.
Yeah,
Mm.
from Padjadjaran University. Yeah, and then also there is the head of research group, namely Atik here, Professor Atik. He's joining us as well. She is. And do you still remember Iwan Hastiawan?
Of
Iwan?
course. Of course I do.
Yeah,
Yes. Yes.
unfortunately, he passed away in
The way
2019.
I know, I know,
Oh, you know
I
him?
know. That
Oh,
was
you
really
know this
sad.
news.
Yes.
Hmm.
Yes. Yes.
Okay, and
Yes.
I'm still working with palladium chemistry as well. So
Oh, you
in
do. Are you still
palladium.
collaborating with someone from Germany?
Yes, still, I'm going to visit Wurzburg again with Professor Radius, yeah, Professor Udo Radius
Oh,
from
nice.
Wurzburg.
Mm-hmm.
Yeah, and
So when
we
will you be in
still
Würzburg? When?
October, inshallah.
Oh, wow. I will be in Würzburg in October as well.
Okay, so then
Yes.
I hope to see
And
you there. Yeah. I
yes,
will
let
do
me
some
see.
whole
When? Let me
seminar.
just, yes. I will be there. Let me see. From 9th to 12th of October.
Okay, and then I will be scheduled to give a whole seminar on 12 in the Wurzburg
That is,
in the Institute of
that is,
Inorganic.
but 12th, isn't that the Sunday? It
I
is a
forgot,
Sunday.
but has been scheduled. I forgot, but it's somewhere around 12 or 13. I think 14. I forgot, but
Okay.
I have been
Yeah,
invited by Radius, yeah, to give because we are still collaborating.
oh, very good.
We did some publication about CHR relation using palladium
Mhm.
chemistry, palladium catalysis,
Nice, nice. Yeah. So
doing
maybe I
some.
will see you when you are there. So when are you arriving? Do you know that already?
1 October, 1st of October, I will be there.
Ah, okay. And I will
Yeah.
be there from Wednesday in the evening, the 8th of October, until
Okay.
Sunday, 12th of October in the evening. We have a
Okay.
meeting from our
Meeting
boron nutrient capture therapy group.
European. Okay, with Todd Mother.
Well, no, Todd Marder is not working on BNCT. He is just a
Oh,
boron chemist, and this is focused on the treatment for cancer, boron nuclear
cancer.
capture
Okay.
therapy.
So you
So
will not. So you were invited by the medicine department.
it's really our society, and I'm the vice president. So
Oh yeah, I saw it in your CV, short CV.
yes,
Yeah,
and so that is our
because
annual meeting.
hmm, okay, I see. So will you visit the Institute of Inorganic as well?
We will be in the new meeting for boron compounds and
From Markham.
energy
Okay.
materials. Yeah. So that is the first part. We will be there on Thursday and Friday. And then on
Okay.
Saturday and Sunday, we will be at the medical hospital
Medical
in
hospital.
Würzburg.
Okay.
Yeah.
In Grombol,
It's two
Yeah.
events. Yes.
Hmm.
It's two events. Yeah.
The events
So I
so
will I
still
will maybe
very active. You are
yes.
very
So
active.
so yes. So let me know if you can come and visit our meeting on Thursday and
Yeah,
Friday if you're
sure,
there.
sure.
Mhm.
Because Boron Center is there in Westbrook. There is
Yes,
a
it's
Boron
on the
Institute.
campus.
Yeah,
Yes,
yeah, on the
it's on the
campus. Yeah,
campus. It's beautiful. It's a really nice institute. Yeah.
chaired. Yeah, chaired by Professor
Braun-
Braunschweig,
Braunschweig.
Holger. Yeah,
Yes.
you know him, Holger.
Yes, of course. Mm.
Yeah. Okay. So hope to see you there in
That
October.
would be nice. Yes, that would be
Okay.
nice.
Yeah, keep in touch.
hmm hmm
Yeah, I saw your tweet on the X as well. I see what's going on your research.
Yes, I'm not using X so much anymore because well, it's sort of well, when it was
Hmm.
Twitter, it was more independent, and now as X, it's not so
Okay,
independent
I see.
anymore. And so yeah, so
Okay.
I'm using LinkedIn. Um,
Okay.
Yeah. Sometimes Instagram, not so
LinkedIn.
much.
Okay. I'm
Yes.
not really active in the LinkedIn actually.
Oh, yeah, you
Unfortunately.
should. LinkedIn is a good platform. Yes. Okay. So at what time are we starting?
Okay. I think after 1:10. Actually, is it okay? 1:10. Yeah, I will start 2
Yeah,
minutes left.
around one
Is it?
time. Yeah, we have our president, the head of Indonesian Chemical Society, Prof. Adi Darmawan. Hello, Prof.
Prof.
Adi.
Adi Darmawan. Oh yeah.
Oh yeah,
Can you hear me?
I can see his tile, yes. And the picture. Yes.
He is the chair of our chemical society, Indonesian Chemical Society. And Professor Mitri is the head of our division, the inorganic division. So you're supposed to be proud of this situation.
This is my mistake, Prof. Because nobody won.
No, these things never by mistake, never.
And Yudha is the general secretary.
Yeah,
So
I'm the
it's
secretary
the
of
whole
course.
division. The most important people are here. Very good.
Prof, as I applied the idea invitation, it was rejected, and they give like not clear reason. Maybe because I wrote in this or Prof, I forgot the name. Maybe
I don't think so.
Prof Vegan wrote that he was colleague from Professor Hawking, blah blah blah, like that. And I think like hierarchy, I think. And I don't know why they reject it.
No. I mean the DAAD, they had tremendous cuts in their programs, so the financial support sort of is not as high as it was before, and so I think they stopped. When you look at the internet, when you Google DAAD and cuts, then you will see that they have, I think, stopped about 20 programs, and in other programs reduced the number of scholarships. So it's probably that. Maybe just apply again next time. Yes, just apply again.
Yes, you will see.
Yeah. Because you know
Okay,
that, yeah, okay.
Okay, I think shall we start? I think we can start now. So I would like to say welcome to participants to attend the inorganic talk currently this month. And before going to hear about the chemistry from Eva, we'd like to hear the special remarks from the head of inorganic division, Professor Witri. So, Professor Witri, time is yours.
Yes, thank you, Dr. Yudha. Good afternoon, my colleagues here, and students and distinguished guests. A special lecture here. We have guest here, Professor Hey-Hawkins. She is from Leipzig University and from Babes-Bolyai University, Romania. Yeah. And it is my great pleasure to honor and welcome you all today in Inorganic Talk webinar hosted by Inorganic Chemistry Division of Indonesian Chemical Society. This event is part of our ongoing commitment to fostering scientific exchange, promoting innovation, and advancing knowledge in the field of inorganic chemistry. And today we are especially privileged to have with us here a renowned figure in the global chemical community, Professor Dr. Honoris Causa, mult Evamarie Hey-Hawkins. She is actually emerita from Leipzig University and also affiliated with Babes-Bolyai University. And Professor Hawkins has made exceptional contribution to the field of organometallic and coordination chemistry, and her groundbreaking work continues to inspire scientific around the world, especially for female scientists. Yeah. And then her lecture today with the title Heterobimetallic Complexes for Application in Homogeneous Catalysis touch us on a topic that is both timely and highly relevant. The design and application of heterobimetallic complexes hold immense potential in addressing key challenges in catalysis. particularly with respect to selectivity, reactivity, and sustainability. And on the behalf of the entire division, I extend our deepest gratitude to Professor Hey-Hawkins for accepting our invitation. We also thanks all participants for joining us today and for your continued enthusiasm in advancing the frontier of organic chemistry. And let us turn to our attention and insight and inspiration that await us in this exciting moment, or exciting event. Thank you very much, Dr. Yudha. I give the time to you.
Okay, thank you so much to Professor Vetri for the remarks. Then, before going to hear about the chemistry from Professor Eva, I would like to show about his CV, her CV, her short CV. Okay, let me share her CV, short CV. So this one. So I hope that you can see the monitor, the screen clearly. Yeah, Mbak Fitri ya. Can you see the
Yes.
screen? Okay. So here is Professor Evamarie Hey-Hawkins. He is well-known professor in organic chemistry and also in Indonesia because she visited Indonesia several times, including our university, in Bandung, in Padjadjaran, Jatinangor. When I tried to browse her name, Evamarie, she visited several universities in Indonesia. So it's supposed to be not very. Her name is very common in Indonesia right now, in organic chemistry topics, researchers. And then she was the professor of inorganic chemistry at Leipzig University from 1993 to 2023. So already 30 years spending time as the professor of inorganic chemistry. Then she already retired, but she's still active in several institutes, like Institute of Bioanalytical Chemistry, and also she received some education. So she received diploma in 1982 and doctoral degree in 1983 at the University of Marburg, Germany. Yeah. Then she visited some university for the postdoctoral position in the UK, yes, Sussex University, the University of Western Australia, 85, 86, and the University Canberra, Australia, 86 to 87. Also, and then afterwards, she completed her habilitation in Marburg in 1988. Yeah. Then afterwards, she held the full professor in the University of Leipzig. Also, she received some distinguished award in the chemistry society, such as Distinguished Woman in Chemistry and Chemical Engineering by IUPAC. Also, so this is why the Professor of Witri also received several awards in term of woman in chemistry as well. So apple doesn't fall far from the trees, I think. Okay, and then she also received some other medal or awards, and also her research focused on organophosphorus chemistry, biological active boron compounds, and heterometallic transition metal complexes and catalysis. So she produced more than 100 doctoral students and from her group. So she has authored more than 600 publications in referred journals. So currently she is the head of the IUPAC, German Central Committee for Chemistry. So then also vice president of the German Society of Boron Neutron Capture Therapy and project leader at the Department of Chemistry at Babes-Bolyai University, Romania. So I think it is a big honor for us to receive you as the speaker in our inorganic talk currently. So I think I would like, I don't want to postpone your talk more. So I will give the stage to you, Professor Eva. So time is yours.
Thank you. Thank you very much, Dr. Buddha. Yudha, and of course also to Vitri for inviting me and for giving me this opportunity to talk to you today about one of the topics that we have been working on, that is heterobimetallic complexes in homogeneous catalysis. And you know that I've been to Indonesia, as you mentioned, several times. It was always a pleasure, a beautiful country, beautiful people, beautiful science. And of course, Vitri, one of my former students, is doing extremely well. And so, of course, I'm very proud of her. So looking at the topic today on heterobimetallic complexes, of course, this is related to catalysis. And this picture here on the right-hand side that is summarizing what a catalyst does, more or less, is very important and has become more and more important in many areas in chemistry, in synthesis, pharmaceutical chemistry, and others. So what typically happens is that when you do a reaction, you start with the reactants and then you go to the products. Typically, this is a reaction where delta H, the reaction enthalpy, is negative. So you have a driving force, but you have an activation energy. And so if this is very high, the reaction is not going to proceed, or you have to heat it or irradiate it. You have to introduce energy. If you have a catalyst, then this profile changes. The catalyst reduces the activation energy, and it can do this in several steps, sometimes only one step, sometimes several steps, but the activation energy is lower. And so we need less energy to conduct a reaction. And of course, this is very important. Nowadays, the toolbox in catalysis has expanded a lot. So there are many metals, there are many ligands that can be used for catalysis. And of course, as you see, energy is always a topic that is in everyone's area now. We have to reduce the energy that we use to make new compounds or to destroy compounds that we want to destroy. Of course, nature has done this already for the long time, has evolved, has produced catalysts that can either make compounds at room temperature, at normal pressure, under conditions in water, or can destroy compounds under the same conditions. And so learning from nature is very, very important. Now, what kind of catalyst does nature have? There are many, and I'm only giving you 4 areas here. The first one is clusters, like the ferredoxins or the manganese calcium cluster here, for electron transfer reactions and in the photosystem that produces oxygen. Dinuclear compounds where you have 2 metals, and they are typically there to facilitate multi-electron steps, like this iron or the iron-nickel complex here. Then there are compounds that act through space, where the 2 metals are apart, but not too far apart, so that they can still synergetically interact and, for example, activate substrates, like in this nitric oxide reductase or the cytochrome C oxidase, or, and this is what we are looking at, compounds where the metals are in the protein structure. These are the amino acids, the side chains of the amino acids, and are connected by a spacer so that they have a certain distance and a certain arrangement. And I'm just naming 2 here, the zinc copper superoxide dismutase and the alkaline phosphatase. So let us look at this one, the superoxide dismutase. This is a really well understood metalloenzyme. It is a dimeric compound, as you can see here, and this is the active site. And if we look at the active site, then you can see that this is the copper center, copper 2, zinc 2. These are the amino acids that connected to the backbone, to the protein that you can see here in the band structure. And this is copper 2 with the water molecule coordinated, and the zinc is in a tetrahedral environment. And the 2 cations are coordinated via this histidine anion. This metalloenzyme destroys superoxide. So superoxide is one of those reactive oxygen species that when formed can be very harmful. And so it can be destroyed by either oxidizing it to oxygen or reducing it to hydrogen peroxide. And this is exactly what this enzyme does. This is the catalytic cycle. And as you can see, only the one metal, the copper, is important for the whole reaction. It coordinates the superoxide, transfers an electron from the superoxide to copper 2 to make it copper 1, forms oxygen. Then the copper 1 interacts with superoxide here, Now the electron is transferred back to the superoxide, making peroxide, and so it's only the copper that is active. But the zinc is important because it keeps everything in place. So it keeps the framework for the copper to facilitate its activity. There are other enzymes like this acid phosphatase that is not a redox active one, but here iron activates water to make a hydroxide, and this close to the vicinity due to the vicinity of the phosphatase here that coordinates at zinc can attack. So here the two metals have to be in close proximity to facilitate this attack. And the third example that I'm giving here is the cytochrome C oxidase. It's the end of the respiratory chain where oxygen that we inhale is converted to water. And this is facilitated by electron transfer from copper and iron. And because you can see that, of course, you need for oxygen molecule 4 electrons, this is facilitated through the interaction of copper and iron with dioxygen. So these are just a few examples where two metals are required to facilitate a specific type of catalysis in nature at room temperature, at normal pressure. Now, of course, chemists are trying to extend this to catalysis in the lab. And so there are two classes of metal complexes, heterobimetallic metal complexes, where you have two different metals, a red one shown here and a green one shown here. And so they can either have an electronic interaction where this metal here influences the catalytic activity of the red metal to activate a molecule and break an XY bond, or it can be a steric scaffolding for metal like shown here with the ligand, so that the other catalytically active metal becomes more active, more reactive, and activates this molecule here by breaking the XY bond. For example, in copper zinc dismutase. It's not the bond that is broken, but the molecule is activated. The second class is class 2, and here the two metals are important. Here the two metals are in vicinity, and either you can have sequential catalysis, where the first metal converts molecule X to Y, and then the second metal takes this molecule Y and converts it to Z. So this is called sequential tandem catalysis. And in the third example, and this is more like the cytochrome C oxidase, we have synergistic catalysis, but the two metals act synergistically and activate a substrate where one part reacts with one part of the molecule and the other with the other. Okay, so these are typically examples of heterobimetallic catalysis, and today I'm going to show you especially in the second part, an example for sequential catalysis. And in the first part, it's more like the scaffolding for one metal to facilitate catalysis, and you will see how we do this. So to have a multi-metal catalyst, of course, gives you much more possibilities. If you have just one metal and a ligand, it is a more or less two-dimensional variation that you can do. But if you have a second metal, then you suddenly have a three-dimensional space, and you can virtually have immense number of possibilities where you can tune the catalytic activity of the metals, where you can tune the catalytic activity of one metal only, and thus extend the scope tremendously. And this is why dimetallic complexes with two different metals are typically now very important in catalysis. Examples from literature. Here you have a homometallic organometallic diiridium complex, a homometallic dipalladium complex, and a mixed one. You can see the left half is from iridium and the right half is from palladium. And only this mixed metal complex catalyzes this two-step reaction, the dehalogenation, palladium catalyzed, the transfer hydrogenation to make this alcohol that is catalyzed by iridium. You can also do Suzuki-Miyaura coupling, where you have a CC bond formation using this aryl bromide and then followed by transfer hydrogenation, iridium catalyzed. Or you can first do the Suzuki-Miyaura coupling and then do alkylation to make this alcohol. But you need this mixed metal catalyst. If you just use one of them, it would catalyze only one of the steps, and even a mixture can be used, but this is far more efficient because the metals also influence each other. Second example is this rhodium-aluminum complex that was used in the literature. Here is the reference to selectively replace a methoxy group in an aromatic system like here, here, or here by proton or by a boral unit that can then, of course, be used in other catalytic steps. And these reactions have been studied, and you can see the scope here. So this is a tremendous scope where this catalyst can be used. And the reason why it is very selective only for this methoxy group, of course, is the vicinity of aluminium and rhodium. The catalytic cycle is shown here and was also published in texts by these authors. The aluminium is a very, very oxophilic element. It interacts with the oxygen atom of the methoxy group, and this brings the ipso carbon atom here in the vicinity of rhodium. And so it is a synergistic effect, as you saw in class 2, of both metal atoms activating the carbon-oxygen bond here and finally cleaving it to make a methoxy group and the ara group. And then in the second step, this silane that has a hydrogen atom reacts and gives the demethoxylated aromatic system. And the scope, as you can see here, is really, really good, and it can also tolerate a lot of other functional groups. So this, of course, is only due to the fact that there are two metal cations in the catalyst that can do this catalytic conversion. Now we are looking at different problems. In the first part of my talk, I will tell you about our approach to do CO2 reduction and how this is done or facilitated using a heterobimetallic catalyst. And of course, you know that nowadays using the fossil fuels and burning the fossil fuels generates a lot of problems, specifically with the high CO2 contents in the atmosphere. And so to reduce the carbon dioxide in the atmosphere, you can either plant more trees, but that is limited, or you can try to do this catalytically. If CO2 increases further, we will have an even more severe climate crisis as we have now, because the CO2 prevents the radiation that hits the Earth from the sun to escape again and sort of warms up the atmosphere, and so we have rising temperatures. So to reduce CO2 to something useful would be very, very helpful. We are doing this with a heterobimetallic catalyst, and we want to convert CO2 to something that can be useful. And so to hydrogenate it, as you can see here, add the hydrogen, add CO2, facilitates the formation of formic acid. And formic acid, of course, is one of the compounds that can be used in chemical industry for many other purposes. This is what we do. Carbon dioxide, the hydrogen, in the presence of a base catalyst, facilitates the formation of this formate anion, because the base abstracts one of these hydrogen atoms, this one here, to make the formate anion. We use a ditopic ligand. You see one pocket here has 3 phosphorus atoms. The second pocket here has a nitrogen and a carbon atom. And we use the group 6 metals, chromium, molybdenum, and tungsten, that are coordinated in this tri-coordinate way by the phosphorus pocket. And we use iridium, rhodium, and cobalt in the other pocket, group 6 metals, that is now coordinated through carbon and nitrogen. And then what we did was we wanted to try to understand the interaction between these two metals, how they do this catalytic reactions. And we wanted to see if the two metals are interacting, because you saw we have class 1, we have class 2, and so we wanted to see what kind of catalysts we have if this catalytic reaction works. And now this is a very systematic study, and so the first part is more or less to show you how research is conducted to really facilitate an understanding of the catalytic behavior of your complex. So first we have to make the ligand. This is a multi-step synthesis that is all organometallic chemistry, where we take the chlorophosphine, dibromobenzene, introduce the phosphonyl group here using a lithiated Grignard reagent, and then in the next step, we react this with phosphorus trichloride to put 2 of these moieties on the phosphorus. In the next step, we use the lithiated aryl pyridine moiety here to build up the second pocket. And typically phosphorus NMR is a very nice way of studying these compounds because these two phosphorus atoms are identical. They're coupled with this phosphorus atoms give a doublet. And this phosphorus atom couples with these two identical ones to give a triplet. And so we see the coupling in the phosphorus NMR spectrum. Now we make the complexes. And so first we introduced the group 6 metal, chromium, molybdenum, or tungsten using the hexacarbonyls. They are commercially available. They can be activated using this trimethyl N oxide that weakens the bond of the metal carbon unit here to produce a carbon dioxide. So you have a vacancy, and this is reactive enough to then form this complex where 3 CO2 groups are lost. In the second step, we reacted with the metal cyclopentadienyl chlorides, and this is the pentamethyl cyclopentadienyl ligand. This is Cp star, and we extract a chloride here to facilitate reaction with this CH group. So this is CH activation and HCl elimination with the presence of the base here, sodium acetate. And in the final step, we need to get rid of this chloride here to make the group 9 metal catalytically active, and this is done using sodium hexafluorophosphate. And this then gives us this cationic complex here with PF6 as a counterion. Rhodium and iridium complexes can be made this way with all 3 group 6 metals here, but the cobalt complex needs different conditions. Here we take the cobalt 3 cyclopentadienyl trisnitride complex with 2 counterions. The CpN is giving the third counterion for the cobalt 3+. And so we have the 9 complexes here with the 3 group 6 and the 3 group 9 metals and all the combinations. So this is the synthetic part. The second part is, of course, we have to see if having 2 metals in one complex is different from just having a combination of 2 monometallic complexes. So we made the monometallic complexes as well. And you can see here, this is just a phenyl ring and not the pyridine coordinated. So monometallic one. And then the second half, this part here, just has the phenyl ring and not the carbon phosphorus bond. And of course, this is to see if the combination is different in catalysis than the separate moieties or a combination of them. When we look at phosphorus NMR spectroscopy and IR spectroscopy, what we already saw was that this moiety here is very similar to the moiety in the heterobimetallic complex, and this moiety here is very similar to the heterobimetallic moiety here. And so this more or less already indicates there is no interaction between the 2 metal centers, because we would see, for example, in cyclic voltammetry, an influence if there was an influence of one metal on the other. And just to show you that this is really not the case, I'm having the metal cobalt, molybdenum cobalt combination here, and the 2 monometallic complexes, and in cyclic voltammetry, you can see here in black just the cobalt. You can see the cobalt reduction, cobalt 3, cobalt 2. You can see in blue molybdenum, the oxidation, molybdenum 0 to molybdenum 1. And then in red, you can see the combination for the heterobimetallic complex, and you can see it's really only just the same as the 2 monometallic complexes. And this means, and even if we look at the redox potentials, they are very, very similar. There is no communication between these 2 metals. So we would have something like the class 1, where the scaffold gives the activity for the second type of metal. Yeah, okay. So this is already an indication. Now we study the complexes, and the first, of course, is that we need to see the influence of the group 9 metal. So we leave the molybdenum there, and then replace the cobalt, rhodium, and iridium in the second pocket. What we see is that the iridium-molybdenum complex was the most active one, as indicated by the turnover number. And this gives you, it's not an extremely active catalyst, but it converts CO2 with the hydrogen to the formate salt. And the catalytic activity is clearly higher for this combination, molybdenum and iridium. Then, of course, we have to see if the group 6 metal also has an influence. And so we varied the group 6 metal, keeping iridium, as this already proved to be the most active one, in place. And what we saw was no really clear trend, but the chromium complex is definitely the least active. The tungsten complex is not very active, and the molybdenum-iridium combination, again, is the most active. And so we focused on this. So these experiments were conducted just to find the best catalyst for our reaction, to then study this catalyst and optimize it further. So these 9 complexes have been studied first, and now, of course, we have to see how to scan the reaction conditions. So if we do the catalytic reaction, besides the catalyst, we need a base, we need a solvent, we need CO2, and we need a hydrogen. And so we scanned the solvents, we scanned the base, we scanned the pressure of CO2, and we scanned the pressure of the hydrogen. And what we saw was that acetonitrile, a solvent, was the best between the 5 solvents here. TMG, that is tetramethylguanidine, is the best base, followed by DBU. And then these are also good bases, but this is the best base. And then the CO2 pressure and the hydrogen pressure, the higher the pressure, of course, this is limited by the autoclave that we are using for the reaction, but the higher the pressure, the higher the turnover number. And so the catalytic activity was optimized using acetonitrile as a solvent, this base, and then, of course, a high pressure. Okay. So now, of course, we have to prove that the heterobimetallic system is different from the homometallic systems. And so we studied the molybdenum complex, and you can see the molybdenum complex is not catalytically active. The turnover number is 1, and so there is not a catalyst. One molecule converts 1 CO2 of the catalyst. If we use iridium, just the second half of the heterobimetallic system, you see the turnover number is 20. So with this molecule, we can already convert 20 molecules of CO2 with 1 molecule of this iridium complex. Yeah, so the turnover number is not tremendously high, but it's catalytically active. But the combination of the 2, molybdenum and iridium, is more or less just the catalytic activity of the iridium complex. But when we use the heterobimetallic complex, you can see the turnover number now is 130. It's not an extremely good catalyst, but it shows that the approach to use 2 metals, to use the molybdenum to scaffold the environment for the iridium, really makes sense and makes a better catalyst than the monometallic complex itself. Yeah. And so this is the catalytic activity. This is the best catalyst, but remember, the 2 metals are not communicating electronically. We showed this by cyclic voltammetry. This is the catalytic cycle. And of course, after we've optimized everything, we had to understand the catalytic cycle. So this is typically the systematic approach. When you've optimized everything, you have to understand how the catalysis works. You do this using DFT calculations, you do NMR experiments, you do kinetic measurements, you isolate intermediates like this hydride complex here, or the formate complex here. You do stoichiometric reactions just to see if this is really converted as you propose it in the catalytic cycle. And then you can propose a catalytic cycle in the end. So this is a lot of work, but if it's done properly, then of course you get the cycle. In the first step, you have the base that we need to abstract a hydrogen atom of our formate, formic acid, to make formate. That is the driving force. And of course, this base will coordinate at iridium. So this is why the base is so important, and why finding the right base is important. The base will coordinate no matter what, but if we have acetonitrile as the solvent, then it can replace the tetramethylguanidine to some extent and form the active catalyst. The next step is the hydrogen activation. The hydrogen replaces the acetonitrile, coordinates side on, and so this is the very important step. We need the base to abstract one of the hydrogen atoms, and this was confirmed by experiments and also by theoretical calculations, to abstract a proton and heterolytically cleave this bond. So the hydride stays with the iridium, and TMG forms the cation, the tetramethylguanidinium cation. This has no barrier, so this goes all by itself, but the next step, that is the rate determining step. The approach of the CO2 to transfer the hydrogen atom to this carbon atom here, followed by cleavage of the iridium-hydrogen bond and formation of the iridium-oxygen bond to form the iridium formate. So this is the rate determining step. And this, as you will see, is what gives the activity, the highest activity for molybdenum iridium, as I will show you on the next slides. And then, of course, the formate has to lose the complex, and so the ion pair formation is the driving force, and then we start again. So this is our catalytic cycle. As you can see, we have proven every step, and so this is really what it looks like. But the hydride transfer is the rate determining step. So somehow this energy must be lower if this goes faster for molybdenum, because this is more or less the same for cobalt, for chromium, molybdenum, and tungsten. So why is molybdenum the most active one if there is no communication between the two? Well, there is no interaction between the two metals. The distance between the two metals, and this the crystal structure of the hydride complex, the distance is just too far. So the electronic communication, interaction through space is not possible. So what is the answer? The answer is in the molecular orbitals. The CO2, this is the highest occupied molecular orbital of the CO2, has to interact with the LUMO of the metal hydride. Remember this step here, where CO2 interacts. And so if we look at the HOMO, sorry, of CO2, then you can see the LUMO of all of these complexes, they look virtually the same. So they can interact rapidly with the LUMO, and you can see this fits quite well, yeah, with the LUMO of this moiety here, and also with chromium. So this cannot be the answer, because HOMO-LUMO is the first interaction. So it can interact with chromium, molybdenum, and tungsten. But when we look at the HOMO, in the chromium complex, the HOMO is delocalized through the whole molecule, and here the HOMO is localized on the molybdenum. The same for the tungsten. And so this means that if CO2 approaches, we have HOMO-HOMO repulsion here. And so here, the repulsion sort of does not allow the CO2 to approach, but in molybdenum it does. For tungsten, it also facilitates the approach, but for tungsten, the tungsten formate bond is much more stable. So the last step, the release of the formate, is less pronounced or less prone to happen than in molybdenum. Yeah? Okay. So this was a very, very intensive mechanistic study where we showed that this heterobimetallic complex, after we synthesized it, we've proven that the heterobimetallic moiety is most active, that it has a synergistic effect due to the molecular orbitals that I showed you. We've optimized the catalytic conditions. We've elucidated the mechanism. We've assessed, I haven't talked about this, that this is a homogeneous catalyst. And of course, in the last step, we've shown that the molybdenum-iridium combination is the most active one, because when the CO2 approaches in the rate determining step here, in the hydride transfer step, this interacts with the HOMO of the heterobimetallic complex. There's repulsion, and so this is why in the case of the chromium, this is the slowest working catalyst for all of them. Okay. In the second part of my talk, I will show you some tandem catalysis, where we have used two metals in heterobimetallic system to facilitate a very nice synthetic approach, and I will show you that this can be used to make one of the anti-cancer drugs that is on the market today. The ligand that we have made, and this is always the first step, you have to think of a ligand that you want to make, and then in the next step you have to make it. And the ligand that we have made here has a tri-nitrogen pocket and a tri-dinitrogen phosphorus pocket. And of course, this nitrogen atom is a hard, according to the Pearson scale, and this phosphorus atom is soft, so we have a hard and a soft pocket. We have modified the R groups here on phosphorus, phenyl and T-butyl, because the donor acceptor properties of phosphorus can be tuned based on the substituents on phosphorus. And then we have used the two pockets to selectively coordinate a hard metal manganese, iron, cobalt, nickel, copper, and zinc. So this is the 3D metal series from group 7 to group 12. And we have included here, and I'm only going to focus on palladium today because palladium for catalytic reactions is really important. And then we have used this complex, the heterobimetallic complex, to facilitate conversion at palladium, and used this product to facilitate the second reaction step to facilitate product formation. So you need two metals to really make the product, and I will show you how this is done. Ligand itself is easy to make, so we use this molecule, we make it in bulk scale. It's a hydrazine moiety where this NH2 group readily reacts with a aldehyde function. This is a shift-base reaction. So if we use an excess of this, then we can introduce the pyridyl moiety to make the NNN pocket. This is the AB fragment. And then in the next step, we've made this phosphonyl substituted aldehyde, reacted it with the second amino group here to make the PNN pocket. So this is our ligand with the phenyl groups at phosphorus and the T-butyl groups. Then we have used the phosphorus pocket here to guide palladium specifically into that pocket. And this is why phosphorus is important in this part, because if we use these ligands here and react them with a palladium precursor, palladium will exclusively select the pocket with the phosphorus atom because palladium 2 is soft, and so it will exclusively only enter this pocket if we do the 1-to-1 reaction. These are the precursors, palladium dichloride, cyclooctadiene, or the C2-nitride complex with triflate, non-coordinating triflate counterion. So this is the triflate counterion. In the second step, we've used the metal triflates of the metal 2 series here, and these then selectively fill the second pocket. So you can use this heterodiatopic ligand because it is selective for the two different types of soft and hard metals to selectively make these heterobimetallic complexes. And the palladium pocket, of course, has the palladium, has the ligand, has an anion because this is coordination number 4. And it's typically always 1-to-1, at least in what I'm going to show you today. And the second metal, the metal 2 here, the same, the ligand coordinates it, a tridentate coordination. It has anions coordinated. And of course, we can now check the intermetallic distance by X-ray crystallography. We can check the electrochemical behavior to see if the two metals influence each other, and so on and so forth. And they do. Okay. In the case of the phenyl derivative here, the reaction goes exactly as we wanted it to react, and we can see the chemical shift of the phosphorus atom goes downfield because now we have it coordinated at palladium, and so from -14 it goes to 30.8, and this is typically always a sign of coordination. This is the crystal structure. You can see this nitrogen atom coordinates, and we form this square planar moiety with a chloride. When we use this T-butyl complex here, T-butyl is a very electron-donating phosphonyl moiety, and when we do this, we observe that the palladium does not coordinate to this nitrogen atom here as it did on the previous slide. So this is the nitrogen atom where palladium coordinates, but here CH activation, because palladium is a catalytically active metal, CH activation occurs, and we form this palladium complex where now we have a palladium carbon bond. And this reacts with hydrogen chloride to form the pyridinium salt. Of course, we don't want this because we need the nitrogen to introduce the second metal. So we react this with the base, and this deprotonates and forms the ammonium chloride, triethyl ammonium chloride, and deprotonates the pyridine. And both compounds have been structurally characterized, so you can see the HCl interaction here and also the pyridine. So now we have this monometallic palladium complexes, and now we can make heterobimetallic complexes. Today I'm only going to show you, for the sake of time, the formation of the manganese and cobalt complex with a palladium complex that has the nitrogen coordination here. This goes well. We form the palladium manganese heterobimetallic complex. Manganese goes into this pocket here. Octahedral coordination for manganese, square planar for palladium, and manganese is coordinated with triplet, and the chloride, the counter ion here, also coordinates at manganese. So we have a Zwitter ion here. Palladium is formally plus, and manganese is formally minus, because this is manganese too. The cobalt complex is a dimer, but a similar feature is observed where we have palladium with one chloride. Cobalt grabs the second chloride and has a triflate, but forms this dimeric compound. When we do the same reactions with the palladium complex that now has the palladium carbon bond, we form the heterobimetallic palladium manganese complex, and look at the distance. The distance is 6 angstrom. And when we do the same reaction with the cobalt triflate, cobalt-2 triflate, then the structure bends a bit more and the distance is a little bit smaller, because now the palladium, due to the fact that it's coordinated to carbon, can approach the cobalt atom here in a better way. And the whole arrangement is more twisted. So 2 metals are better than 1, definitely are, as you will see in my last slides. Palladium has been used in catalysis, has been awarded a Nobel Prize for catalytic reactions to several scientists. And you can see here Negishi coupling, Suzuki coupling, and so on and so forth. And so palladium 0 activating a metal halide bond, and then transmetallation giving you, in the end, by reductive elimination, element-element coupling, is one of the most used reactions in organic synthesis. And this is just another catalytic cycle. This is why we use palladium as one of the metals in our pocket. Now, when you look at the complex here, and I'm only showing you the one where we have the CH activation and the palladium carbon bond formation here, we have the heterobimetallic complexes with manganese and cobalt. Of course, to show that the heterobimetallic complex is better, we always have to make the monometallic complex to really show that it's better than that it's not better than the combination. And we have to make the monometallic ones. Same approach as I showed you in the first part, where we just have this part of the molecule with the 3D metal, and this part of the molecule here with the palladium. Okay. Then we use these 4 complexes, or 5, 6, 7 complexes, 6 complexes in the Sonogashira coupling, and we use the copper-free approach. So this is just a different way where the palladium takes over the task of the copper in the copper-free Sonogashira coupling reaction. We use this phenyl acetylene and bromobenzene to make a CC coupling product. Okay. The second step we used was the transfer semi-hydrogenation to transfer the hydrogen from ammonia borane, this is our sacrificial hydrogen donor, to this toluene molecule, and to form the Z isomer selectively, because you can have the E and you can have the Z, but the Z, as you will see, is important for the drug that we wanted to make. Okay, so it's a 2-step reaction, tandem catalysis, that will be facilitated, as you will see, by the heterobimetallic complex. The ligand alone is not really catalytically active. This is the first column here. The palladium complex is a little bit active, not with this type of ligand. Here is only the ligands, they are not active. The combination manganese-palladium, this is the gray arrow, the gray bar here, gives us a little bit of the product of the diphenyl acetylene, but not a lot. And you can see the cobalt palladium, when we screened this reaction, is the best. So we continued with the combination cobalt and palladium and try to understand why. The cobalt plane here and the palladium plane, they are tilted. So it's not a completely planar molecule, but they are tilted in this molecule, so that cobalt and palladium can sort of get a little bit closer together. And so that is important. And when we look at the cyclic voltammetry, you can see for the monometallic complex, there is no reduction of palladium observed, no reduction. But when we have the heterobimetallic complex, you can see reduction of the cobalt 2 to cobalt 1. This is the first step. But you can also see reduction of palladium to palladium 0. So the reduction of palladium is facilitated by cobalt. And this then facilitates the whole process. And the cobalt itself is also important because it activates the carbon-hydrogen bond of the phenylacetylene to really drive the catalytic cycle. So both metals are important. And so we have then screened this reaction for several catalytic reactions between phenylacetylene and bromobenzene. This is the simplest one, using ammonia borane after we isolated this in the second step. But of course, if you want to do tandem catalysis, this must also be possible to do this in one pot. And so we used just our pre-catalyst, this heterobimetallic system, and did the first reaction to make the CC coupling with the carbon-bromine bond here. And then in the next step, the semi-hydrogen transfer here to make the Z alkene. And that is the second step. And we did this in one pot using this heterobimetallic complex. Now, the Z to E ratio, of course, is important, and this is given here in brackets. And you can see this approach here was screened for electron donating groups, electron withdrawing groups, groups that have heterocycles, biaromatic systems, and so on and so forth. And you can see the yield is typically reasonably good, and also the Z selectivity is quite good. We can separate the Z and the E isomer if we want to using chromatography. We used this approach, and that is the last slide, more or less, before I go to the summary, to make a drug. Combretastatine A4 is one of the most potent antimitotic agents, so it prevents the spreading of cancer, and it's used in cancer therapy. And of course, with our catalytic approach, we can make this drug in one pot in reasonably good yield using this palladium cobalt catalyst. And you can see that this catalyst is really good because it tolerates the methoxy groups, it tolerates the hydroxy group, and it goes selectively for this iodide, and also the transfer hydrogenation only attacks the CC triple bond to make the Z isomer. The monometallic palladium complex, we tried this also, was not really useful in this reaction and showed very poor catalytic activity. And remember, both metals are important because the cobalt activates the palladium reduction and also activates the CH activation of this alkyne here. Okay, so summarizing the second part, we made this nice ligand, introduced palladium selectively into the NNP pocket, introduced a second metal, a hard metal, a Lewis acidic metal into this second pocket, and then screened for catalytic activity and found that cobalt palladium is the best combination, as they are interacting through space, interacting probably also via the backbone, so that cobalt influences the reduction of palladium to give the reactive palladium zero species that we need for catalysis. We use this in the copper-free Sono-Gashira coupling to make the CC coupling product, the alkyne, and then we made an alkene by semi-transfer hydrogenation reaction. And the nice thing is that our catalyst selectively forms the Z isomer due to the mechanism, of course. The work was done by the 4 very talented students. They've all graduated now and moved on to other areas. Zeno, Wieland, Saral, and Reike. Was funded by several organizations, as you can see here. And of course, I have to thank them for their hard work and for getting these very nice results. And of course, thank you again for inviting me to talk about their research and their results. And thank you for joining me today and for listening to me today. Thank you.
Yeah, thank you very much, Professor Eva, for your very nice talk. Awesome talk. Yeah. I really enjoy your presentation about this heterobimetallic process. Yeah. Complexes as the catalyst, yeah, including the tandem one and the previous one. So I would like to invite the participants to arise questions or discussion towards Professor Eva before myself giving some questions or discussion. So is there any question from the audience? Just raise your hands and we'll give some time for you to give some questions. Is there any question or from the audience? Oh, it's okay. Okay, before having the question from the audience, I would like to learn from Professor Eva. Professor Eva, that most of your tandem catalysts are using kind of pincer geometric ligands. Is there any specific reason why you use that specific ligand type of
Yes.
ligands? Yes, pincer type of ligands.
Yes,
Yeah.
Dr. Yudha.
Yeah.
Very, very
Okay.
important question, because when you make a catalyst, the worst that can happen is that you lose your catalytically active metal. So in many catalytic reactions, the metal is activated by losing one of the ligands, or maybe two of the ligands, or maybe even three of the ligands. And the problem is that if the metal environment is changed during the catalytic reactions a lot, so if it loses any type of ligands, you will change the whole catalytic activity, because the pocket facilitates a specific approach of the substrate, and that is important. So you need to keep the pocket, the shape of the pocket, the size of the pocket, the environment at the metal. You need to keep this intact, and you need to sort of have only 1 degree of freedom, and that in our case really is the metal chlorine bond here, and of course then the axial coordination as well. But you're absolutely right. The pincer ligand facilitates the chelate effect to work, so it makes really, really stable complexes. You will not readily break any of these bonds, because then you sort of lose the thermodynamic stability, yeah, or kinetic stability as well. And so this is why pincer ligands, and this is a very, very nice approach. And we have also made other pincer ligands also for monometallic complexes. This is why pincer ligands are so important and so useful, really just to give the right scaffold, so not to lose the environment that generates the cavity for the substrate to approach. Yes, very well observed.
Okay, thank you, Professor Eva. And from the audience first, having some questions. So you would like to keep the catalyst still stick to the ligand, yeah, Professor Eva?
Absolutely.
Okay, then as a result, that kind of pincer ligand that attach to metal catalysts are mostly very rigid, so that by giving low activity, so that's required high temperature most of the time. Is that true, Professor Eva?
Not necessarily,
Or
because when you look at it, for example,
yes.
let me just go here. So when you look at this type of metal complex that we are making here, you can see that there is always a metal halide bond, for example. Yeah? So this is in one reaction here. And of course, if you now, in the next step, let me go here, or a triflate, or an acetonitrile. So what you need to do is you need to have a metal ligand bond that is less strong and can readily be broken. So in most cases, for example, when we make these complexes, we always have a base. You saw that we always have in our reaction conditions, we always have a base. Let me just go here if I have the conditions. Yes. So we always have a base. Here we have DAPCO as a base.
Yeah.
And this base, of course, typically replaces the anion at the metal that is catalytically active. Yeah. And so that is one way of making a catalyst that doesn't need very, very high temperatures. Of course, here you can see 90 degrees.
Okay.
Is not so high, but of course, sometimes if you go higher, you destroy the catalyst. Yeah.
Okay. Okay, very nice answer from Professor Eva. Okay, so and then you said that the cobalt has function to reduce to palladium 2 to palladium 1 to palladium 0, sorry. Okay. is this reaction still require sensitive toward oxygen, or can be conducted under nitrogen-free situation in that atmosphere free? Because
that is
you have cobalt that has function to reduce the pallium to pallium 0. Then even though there is some oxygen that can oxidize the pallium 0 to pallium 2, but you still have cobalt. Is it still require in the atmosphere for this reaction? Professor.
Yes, very good question, because typically you would want to have your catalyst operate at room temperature in air, specifically the best would be in water. These complexes here, of course, as you observed, the electrochemistry is always done under air-free conditions. So you have to make sure that the solvent, acetonitrile, is free of oxygen, that everything is free of oxygen. Because if you have oxygen, of course, as you said, I mean, oxygen will always be reduced by whatever is being reduced here. So you need to have an oxygen-free environment. The same is true for the catalysis. So the catalytic reactions that you saw, that I talked about here, they are done with exclusion of oxygen to avoid any interference with oxygen. So, but this is typically not a problem because you can use oxygen-free conditions, oxygen-free solvents, so that is possible. But you're right, oxygen messes up the reaction, yes.
Okay. And then how about the side product that can be occur by the presence of other catalysts? Is there any homocoupling present in the mixture or something else?
That is a very good question. Typically, when you have this type of acetylene, phenylacetylene, then of course the CH bond, there's activation. So you make a metal acetylide, and that is typically the task of the copper, in the Zollinger-Schwerer coupling.
Yeah.
And here, this is taken over by cobalt. So the cobalt activates the CH bond, and is not as reactive as, for example, the palladium. And that is one of the reasons why we do observe hardly any homocoupling. So we do not observe the compound where we have two triple bonds, the dialkyne, but this is formed typically in, as you can see here, also this is product of diphenylacetylene. This is formed in very, very high yield. And in the other cases, because I'm giving here the yield of the product only, they are just not very active. So it's not the side product that is formed so that we use up the starting material by forming the homocoupling product. But this is just that these catalysts are not very active. So the homocoupling product is hardly observed.
I see. Okay. Okay, and then how about replacing the cobalt with copper? Because the copper is used as the co-catalyst. Did you do that before?
Yes, yes. We indeed made the whole series. So we made the whole series. As you saw, we sort of went from manganese to zinc. So we also made the copper complex here. And I try to remember why we did not study the palladium copper. Well, the reason was more or less when you look at the last reaction here, where we made the drug. Typically, when you have copper in your catalyst, that is why the copper-free Zollinger-Schwerer coupling is so prominent, because when you make drugs, you do not want to have copper in your product whatsoever. And so the best way of not having copper in your product is not to have it in your catalyst. So yes, you are absolutely right. These reactions here, when you have palladium copper, they would definitely go faster, better. In the first step, definitely. But the second step, the transfer hydrogenation, is better. So the palladium copper combination is better for the first step, for the Zollinger-Schwerer coupling. But for the transfer hydrogenation, the copper is much better than the cobalt is much better than the copper. So these two reasons why palladium copper was not used in making also the drug to avoid copper, and because the transfer hydrogenation is better with cobalt.
Okay. Thank you, Professor Eva. So we received some question from the audience, which is the master students of mine from Padjadjaran University, which are conducting research on polymerization, polyethylene, you give production of polyethylene using some tandem catalyst from Hansa. So he said that thank you. She said thank you for the very insightful explanation, Prof. Eva. She's Hansa and she is currently conducting research on tandem catalytic system. Yeah, she has question in a tandem catalytic reaction. Is it possible for one of the catalysts to undergo deactivation? Second one, does the sequential and simultaneous addition of tandem catalysts influence the final reaction of the selectivity of the catalyst? And the third one, how can the selectivity of each catalyst to what the reaction be determined? Thank you very much. Sorry for having three questions
It's okay,
from
it's
the
okay,
students.
it's okay, Kansa. Yes. Thank you, Kansa. Very important question. So the first is tandem catalytic reaction. Yes, of course. In a catalytic reaction, it will stop. And you saw we determined the turnover number. And the turnover number is how many molecules or how many cycles you can conduct with a catalytically active system. And so sooner or later, the catalyst will deactivate for whatever reason. Sometimes it's the product that builds up in the reaction that is coordinating at the metal, so it doesn't sort of leave and then have the empty site again for further reaction. Sometimes it's the starting material that so there are many reasons why a catalyst can deactivate, and in some cases you can sort of study these reactions, but to isolate a deactivated catalyst is not always easy. In some cases, if the deactivation is simply that you lose the catalyst, so that it's sort of just being replaced from the pocket, as you can see here. So if the metal is just sort of expelled, and that is why we always have to make sure that the metal is still in the cavity. So yes, in tandem catalysis, it is possible that just one of the catalysts undergoes deactivation, but then as you need both catalytically active sites to do the formation of the product, then the whole reaction will not give you the product, but maybe only the intermediate. And sooner or later, the second metal will also be deactivated. So a catalyst dies sooner or later. It will never ever go on forever. And just the turnover number or the turnover frequency, how fast it does the conversion, is very important, is a very important number and tells you a lot about the deactivation. The second question is sequential and simultaneous addition. You saw that in these reactions here, what we have done was we isolated the intermediate and then did the second reaction separately. So this was a tandem catalysis where we isolated. And of course here, because you isolate, you purify, you have a much cleaner starting material, because the starting materials for this reaction, the alkyne, the aryl halide, they are no longer in the reaction mixture. Here you just have this as the starting material. Typically, if you do this in a sequential reaction, it will give you a better result. But you have to consider a one-pot reaction is faster, is nicer, so you don't have to isolate, you don't have to work up. And if the starting materials are cheap, if your catalyst is cheap, then typically you would always prefer the one-pot reaction to isolating an intermediate and then do a second step sequentially, because then it's well, you might as well just use two different catalysts then, see? Because why use a tandem catalyst that uses the product that is formed directly when it's formed to form the product, so that it drives this reaction continuously, yeah? So the selectivity of each catalyst towards the reactant. Not sure if I know what this means. I mean, here, for example, we have two molecules that we want to activate and that we want to use in an element-element forming reaction. And so, for example, in the catalytic cycle that we have here, you can see that, of course, the palladium complex, palladium 0, once it's been formed, will always go for the activation of the metal of the carbon halide bond, or the metal amine is then, for example, in the Buchwald-Hartwald used for transamination. So this is always the first step. So the selectivity for palladium 0 will always be highest for this, and this is just done experimentally and proven by many, many researchers experimentally. But if you, for example, do not have an aryl halide, but for example, if you just have the second reaction reagent here, an alkyne, of course, palladium 0 will also activate the CH bond, but it will go for the carbon halide bond first. So the selectivity with respect to kinetics, what reacts faster, that can be studied, of course. You just take your catalyst, you expose it to a mixture of compounds, and then you just look at what is activated first. So this can be studied by competing experiments, and typically you can get an idea about what a catalyst will go for first. Yeah. I hope I answered your 3 questions.
Yeah, I think you already
Answer? Yeah.
answered the question. Yeah, correctly.
Okay,
I think
thank you.
precisely. Okay. Hansa, if you still have more question or did not satisfy with the answer, you can just raise your hand again. And okay, all my questions have been answered. Okay, thank you, Professor Eva. It's a pleasure, and she's a very active student. Okay. She hope that she can also pursue study in Germany as well. Hansa is very active, helping me to give my to make some proposal as well. And then the next question coming from Professor Wirawan. He is the lecturer from the same university as Professor Witri. So, Mr. Wirawan, Dr. Wirawan. So, yes.
Yes, thank you very
Yeah,
much
okay.
for
You can
the.
give your question directly. Okay.
I hope you can hear me clearly.
Yes, I can hear and
Thank
see you.
Yeah, thank you very much for a very nice presentation. Actually, I'm also a catalysis guy, but from heterogeneous part. But I think I always excited to see the progress in the homogeneous catalysis. I have 2 questions. The first questions, I was wondering, have you tried to replace, for example, cobalt with nickel for transfer hydrogenation? Because I think nickel as well has been reportedly researched that this catalyst can perform transfer hydrogenation. Maybe I missed your presentation somewhere. And secondly, in the page 42, I was wondering that you are doing one-pot reactions. Does it mean that all of the catalysts you combine together in one pot and just perform the reaction, or you do, or you did the one pot reaction, but you add the catalyst sequentially? So yeah,
Thank you. Yes.
That were principally my question. Thank you very much.
Okay. Yes.
Professor
Thank you.
Eva.
Thank you. Very important questions. You saw that we have gone through the whole 3D series from manganese to zinc, and so of course we also made nickel. Nickel, you're absolutely right. Nickel will probably catalyze the second step, the transfer hydrogenation, much better, because nickel, palladium, and platinum in heterogeneous catalysis are the catalyst to activate the hydrogen. Yeah, and so you're absolutely right, but this is the metal. It is nickel 0 in activation of the hydrogen. In our complexes, it's always nickel 2. And so nickel 2, to do the transfer hydrogenation, would have to do some redox chemistry. Yeah, so it would have to either be reduced to nickel 0 to then activate the dihydrogen, or it would have to go to nickel 4 to activate the dihydrogen. And so cobalt, on the other hand, as we showed, is easy to reduce. So it's easy to reduce to cobalt 1, and then, of course, can, for example, oxidatively add dihydrogen to form cobalt 3. So the redox states of cobalt are probably better for this type of reaction. And so I would expect, even though we haven't tried it, but I would expect that cobalt is still better in that step than nickel. But you're absolutely right, you should. The second reason for not using nickel is the same as for not using copper. When you make a drug, there are certain metals that you definitely do not want to have in your product, in your drug, and nickel is certainly one of them, because there are so many people who have nickel allergies. So, for example, if you have steel, nickel-containing steels, there are many people that have allergies for nickel. The second question, if that answers your first one with the nickel, yeah. The second question, here we do this sequentially. So this is why it has 1 and 2. So we do the first reaction, we wait for 4 hours. Then most of the product has been coupled. So this is the first one that forms the alkyne. And then after 4 hours, we cool down to 50 degrees Celsius. We add the ammonia borane and then stir this at 50 degrees Celsius for 50 hours. So it's really a sequential reaction, because if you add the ammonia borane in the beginning, it would mess up everything. Yeah. And so you have to make sure that most of the conversion has already taken place, but you do not isolate the alkyne, you just continue with the second. But it's always sequential, always sequential. And in some tandem catalytic reactions, it's possible to really do this all in one go. So you add all of the partners, but then you have to make sure that the second step does not interfere with the first. And in our case, it would. So this is why we did this sequentially. And you see here for some of the reagents that we used, for some of the aryl halides that we used, we even had to react this longer in the second step. So not only for 15 hours, but for some of these we had to use for the silyl derivative here. So for the deactivating moieties, we had to use even longer reaction times. Yeah, but sequential, yes.
Okay, Dr. Wirawan, I hope that you already get the point.
Yeah.
The answer and
answer clear. Thank you.
Thank you.
okay, thank you so much. And there is question also from Professor Witri. Yeah, Professor Witri.
Yes, thank you, Dr.
Okay.
Yudha. This is very nice lecture, Prof. Hey-Hawkins, about the bimetallic complexes. Yeah. I remember about our last walk with Dr. Wirawan also. We tried to modify zirconium and hafnium bismuth and use with nickel, I think. Yeah. Zirconium and modified with nickel. That's why he asked about the transfer hydrogenation. And my question about the last slide, I think, about instead of catalysis, you also use these complexes for cancer therapy, right? Have you tried or have you tested about the activity of the complexes against the tumor cell or cancer cell? And in these complexes, how is the mechanism how they can destroy the cell? This is if we compare with the cisplatin derivative complexes, for example. I think because of the living group, and they will connect or they will coordinate with the DNA, or how?
We used the complexes to make a known drug, and this is the link to cancer chemotherapy. The complexes themselves were not really made to be used as anti-tumor agents. I think we tested them on cells. I'm not absolutely sure, because we wanted to make sure that they were not toxic. See, because if you work with compounds, sometimes sooner or later you have to study their toxicity. And I think we studied the toxicity, and I'm not absolutely sure, but I think they were not toxic. I think they were not toxic. I can't be absolutely sure. But typically for making complexes to be used as anti-cancer agents, the use of two metals instead of one is a nice and interesting approach for chemotherapy, because typically the mechanism that prevents cancers from multiplying, from proliferating, that is one way to stop the cells from proliferation, and then sooner or later apoptosis kills them, or to kill the cancer cell, to just really kill them, necrosis. You always have the two mechanisms. And when you have two metals in a drug, you can, for example, imagine that one metal facilitates one mode of activity in a cancer chemotherapy agent, and the other another one. But these molecules here, they were really more or less made for catalysis and not really for cancer chemotherapy. But if you wanted to make heterobimetallic complexes, you would try to find a metal with a known activity where the cancer killing activity is known, and then combine it with a different one, so to really target cancer with two mechanisms. Yeah, for example, platinum to go for DNA, and maybe something that stops one of the kinases to form. Yeah, so this would really be very, very helpful in cancer chemotherapy. But in cancer chemotherapy, we do not go for the mixed metals. We go for mixed drugs, not mixed metals. But I agree, the mixed metal approach in cancer therapy is a useful one, is a good one, definitely. But not with these molecules, not with these molecules.
Okay. Yes. And one other question, how can we determine, for example, we want to design to bimetallic complexes, yeah, or bimetallic complexes, and how to determine that these two metal will have good cooperation in acting as a kind of catalytic reaction? Because we in our lab we have a case that if we add one more metal, for example, it will deactivate the activity of the other metals, like that.
Yes, that is a very important question. It's at the moment still a lot of trial and error. So you really just see if your compound is active or not. And then when you find one that is active, you try to understand why. The first part was really to give you an idea how complex it is to elucidate the right catalyst for a right reaction. It is really complicated. And typically it really includes DFT calculations. So you have to understand, once you have done the experiment, you have to use the experiment to then go further, to understand why a specific combination could be better for a specific reaction. So at the moment, people are trying to use artificial intelligence to find elements that are unique to specific type of reactions to predict a better outcome. So now if you just screen papers on catalysis, you might be able to get an idea what kind of combination could be the best for a specific outcome. And so, for example, the pincer ligands, as Dr. Yudha already asked, the pincer ligands, they are very, very good in catalysis because they really keep the shape of the catalytically active site. But at the moment, we are not really there yet to predict what you have to do to make the best catalyst. You still have to start with the experiment, but then once you have the experiment, then this is your starting point. Then you can use all of the methods, calculations, NMR experiments, kinetic measurements. You can isolate intermediates. You can do stoichiometric reactions. And this then gives you a picture to understand why a specific catalyst is the most active and what you have to do, like in our case, what you have to do to modify it. Yeah. But at the moment, we are not really there yet to give you well, hand-waving approach, and this is the best catalyst, unfortunately. But I'm pretty sure that artificial intelligence will be very, very supportive in that respect, very supportive, because it can help us eliminate maybe certain combinations that might not be useful, that others have tested, and it might give us a handle on what could be a better combination in these catalytic approaches. And of course, looking at nature, the combinations that nature uses, those are always a very good starting point, of course. But then to extend to something that nature cannot use, like the noble metals, because they're not abundant enough, yeah, and so evolution has not used them. The noble metals, they can be very, very useful in catalysis. Yeah. Yeah, thank you for the question. Very important.
Yes, yes. Thank you. Thank you, Professor. Yes.
Thank you, Professor Eva. So just one question left from myself. I'm curious about this research. Maybe I would like to implement this as I'm currently doing tandem as well for production of polyethylene. So Professor Eva, so the key of this, the selectivity of synthesizing the catalysis is that you try to create what is it ditopic ligands. One topic is kind of soft base and the other topic is hard base. Then you would like to incorporate the hard with the hard acid and the soft base with the soft acid. Is that correct?
Yes. That is
Professor
one
Eva?
of the, yes, that is one of the approaches where
Yes.
if you want to have two different metals, you must make a ligand that discriminates. So for example, if you have the same pocket here, yeah, then you will never be able to selectively address one pocket only. So you have to make them different. And we did this by just introducing phosphorus. And the phosphorus, of course, makes everything completely different. If you now add palladium, then you can selectively include palladium in this pocket. But if, for example, you add more palladium, then you will also fill this pocket. So palladium will
Okay.
also go here, but only if you use excess. Yeah.
Okay.
So it's just a preference. It's a preference. It's not absolute selectivity. So if you have more palladium, palladium will also go here. You can also start with the early transition metal. You can also start with the red one. It will go preferentially here in the hard pocket, but if you add more, it will also go there.
I see.
And so it's not only making a discriminating ligand, it's also then using the synthetic strategy, one-to-one reactions. And this is why I included the ratio here, the one-to-one reaction and one-to-one reaction, to not replace one or the other metals. So you really need to have the right stoichiometry. If you use excess of the metals, you will also sooner or later kick out that metal. It's just a kinetic effect. Yeah.
I see. Okay, thank you so much, Professor Eva. So I
You're
think
welcome.
is there any question from the audience? So it's very interesting chemistry that I learned from Professor Eva right now. Thank you so much, Professor Eva. I think we already collect okay, some other question from okay, there is
Yes. Sharing the
yeah, I
PowerPoint.
think
Yes, I will send a PDF
okay,
file. I will send a PDF file
PDF file.
to Professor Vitri.
Mm.
Yeah. And so anyone who wants to
Okay.
have it, please, yes. And of course, you saw citations at the bottom. So if you want to learn more, please go to the references and then you can also see more about this research. Yes.
Yeah, thank you so much, Professor Eva, because I just made screenshot many times to collect your to collect the data. I mean, to collect
Yes.
the insight
No.
from your presentation.
I will get rid of the animation and will make a nice PDF file and then we'll send the PDF file to Professor Vitri.
Okay.
Yeah.
Thank you so much,
Okay.
Yes, thank you.
Professor.
Thank you.
Thank you.
I
Thank you
think
again for having me today.
yeah, I think we already have had enough question from the audience. I think Professor Vitri, Professor Eva, and we would like also to give you some the certificate officially through the Zoom meeting to the screen. So because we might send you in hand, but we are separated by subcontinental. Okay.
Nice.
Did you see the certificate?
Yes, thank you. You're going to send it to
Okay.
me by email? I took a screenshot, so
No, I will send you by email.
We
thank
can
you.
send,
Thank you
Okay,
so
yes.
much.
so thank you so much for giving the very nice and very insightful talk. And your presentation will be as well presented in the YouTube. So Indonesian
Okay.
or all chemists around the world will have insight from your presentation through the YouTube. Thank you so much, Professor Eva. I think it's very
Thank you
nice
for having me.
discussion. And also for the audience, thank you so much for having question discussion with Professor Eva. And I would like to give some would like to have picture with the audience as well, Professor Witri, yeah. Because in
Yes, yes.
Indonesia sometimes we will need some documentation.
Of course.
So we'll have okay, so gallery, okay. So I think for the audience, could you please show your camera? Yeah. I mean, switch on your camera and we'll give some screenshot for this event. Okay, please, Professor. Okay, ada Dr. Nanang, Dr. Hari, Dr. Ubed, and the President of our Chemical Society, Professor Adi, Professor Ubed. Okay, we'd like to have some screenshot on three. One and Professor Atik as well. You might remember him, her, Dr. Eva, Professor Eva.
Of course.
Okay, Professor Atik. Okay, on three. One, two, three. Cheers. Okay, and then for the second one, for the next one. Okay, on three again. One, two, three. Okay, Mas Abed. Okay, thank you so much for attending this event, and I would like to also invite you again for the next Inorganic Talk, the 9th one, which will be held on August or July. Or July, okay, July. Okay, thank you so much
July,
for
yes.
attending this event. Thank you so much, Eva, Professor Eva. This is very nice, big honor for us to have your nice presentation. Thank you so much.
Thank you for the
Okay,
invitation and have a good day.
bye.
Yes, thank
Okay,
you.
Bye.
Assalamualaikum warahmatullahi wabarakatuh. Bye.
Waalaikumsalam.
Bye.
Bye-bye. Have a nice evening.
Yeah, evening to everyone. Day to me. It's in the morning.
In the morning
Okay,
in the
bye.
German. Bye. Thank you, Professor.
Bye.